All right, folks, so let's get started. I plan on finishing chapter 3 today, and then the rest of the time this week we'll use to do some midterm practice for our midterm on Thursday, and then, we will start new material on Friday's lecture, chapter 4. All right, so if you don't already, make sure that you have your periodic table and your calculator out. This is a very, very math-heavy lecture. All right, so let's get started. We left off talking about the idea of a mole and how that is just a number to represent a very large collection of atoms or molecules, because typically when we are working with samples in lab, we're working with a lot of molecules and atoms. So we need a unit that can help scale up the idea of an atomic mass unit to grams, something that we can actually measure in the real world. So for the next, this slide, we're thinking about converting between grams of a substance to moles of a substance using the molar mass. And then from there, we can use Avogadro's number to convert to either individual molecules, individual formula units, or individual atoms based upon the chemical formula. So let's practice this. We were given the formula caffeine here, and we looked at, okay, if we are given 1.5 moles of sample of caffeine, how many moles of carbon are there? So we're looking at the whole molecule of caffeine to carbon. So we came up with this conversion factor. 1 mole of caffeine based upon the chemical formula is 8 moles of carbon. And so we get that this particular sample has 12 moles of carbon. So in this next question, it says how many carbon atoms are present in 1.5 moles of sample of caffeine. So we're going to start this off pretty much the same. We're going to start off with what's being given here, 1.5 moles of caffeine, and then convert to moles of carbon within there. So now that we're in moles of carbon, we can actually convert to individual atoms of carbon using Avogadro's number. So do we recall what that number is? 6.022 times 10 to the 23. I do not believe you will be given that number on the midterm. Did someone look at the supplemental sheet that you're given? I do not believe you're given it. So that is a number that you need to know. So 1 mole of anything, so in this case, we are considering moles of carbon atoms. So 1 mole of carbon is equal to 6.022 times 10 to the 23 individual C atoms. It's like me saying, okay, 1 dozen carbon atoms is 12 individual carbon atoms. And then when you cancel all those units, you will get some number, what is it? 7.2 times 10 to the 24 carbon atoms. So there is another way we can kind of convert between grams, moles, and individual molecules or individual atoms in a given substance. And then I forgot to add this point. Let's also think about how much does 1.5 moles of caffeine weigh in grams. So within here, we can use the molar mass of caffeine that is given, where 1 mole of caffeine equals 194.19 grams, all right? And so there is our conversion factor that we can use. So if we start with 1.5 moles of caffeine, so now we're kind of going the other way. We were going the forward direction, moles to individual molecules to individual atoms. Now we're going the other way. Let's go to moles to grams of this substance using molar mass. And really, it's just, if you can inspect the units, you'll see it all come together if you're really clever with your units like we did in chapter 1. So here we're going to use the molar mass. So 194 point something, 194.19 grams, and then that will give you the mass. I think it's 290 grams or something like that. All right, so there are different ways that we can kind of navigate this process. So here are some other questions that kind of build on that. Can you go between grams, moles, and atoms? Or sorry, grams, moles to molecules to atoms of a particular substance. So these ones are a little bit more difficult it's not as straightforward as, converting grams to moles or something. But let's think about, this one's kind of straightforward. How many moles of carbon atoms are present in a 6.95 gram sample of caffeine? So we start with what's given here, and our goal is to get to moles of carbon. So my idea is I will start with what's given, grams of caffeine. All right, we're in grams of caffeine. My goal is to get into moles of caffeine because I want to get to moles of carbon. So here I'm going to use the molar mass of caffeine because that's how, that's why it's all weird. I want to use the molar mass of caffeine because that is the identity of the sample here. I think a common mistake students will make with this question is that they'll use the molar mass of carbon. Because they want, we want carbon atoms. But the detail here is that this mass, 6.95 grams, is the grams of the sample, the mass of the sample, which is caffeine. So we need to make sure that we use the molar mass of caffeine, which is 194 point something, 19 grams is 1 mole of caffeine. All right, and so now we want to go to moles of carbon. So then we use the chemical formula. There are 8 moles of carbon per mole of caffeine, and then there is our answer. So you can see here moles of caffeine, that's what we want, and so this answer is 0.287 moles of carbon are in that sample. So the second question says how many carbon atoms are present in this sample? All right, so this question, we're looking at the same sample. So we're starting this off the exact same way. We're going to start with 6.95 grams of caffeine, convert to moles of caffeine using molar mass, convert to moles of carbon using the actual chemical formula there, 1 caffeine molecule or 1 mole of caffeine is 8 moles of carbon. The last step here, what type of conversion are we going to use to get to actual carbon atoms? Oh, yeah, sure. The answer? 0.287. I mean, if you put it in your calculator, you'll get the answer too, right? Okay. You don't have to depend on me. Your calculator will give you the answer too. So the big difference in the previous question, we got moles of carbon. Let's get actual carbon atoms. So we use Avogadro's number here. So we will use Avogadro's number. 1 mole of carbon is 6.022 times 10 to the 23 carbon atoms. So if you see this, what we're doing here is the exact same thing we did in the previous slide. But in the previous slide, I gave you moles of caffeine, all right? But in lab, there's nothing in lab that can tell you how many moles of something you have. Typically, when you have a sample and you want to figure out how much matter you have, you put it on a balance to measure mass. So in this slide, we are starting with the mass of the sample. We need to use molar mass to get to moles, and then go on further to think about how many atoms are there. And so the answer here is 1.73 times 10 to the 23 carbon atoms. Are people checking me? Because I just have scribbles on. It's right? Okay, great. All right, and so this last one. So this one, we're kind of working backwards. So we went from grams of our sample to individual carbon atoms. So in this example, we are given how many hydrogen atoms we have in our actual caffeine sample. So let's recall what the chemical formula of caffeine is. It's right here. All right, so we are given how many hydrogen atoms we have. So if we think about it, 1 mole of caffeine equals how many hydrogen atoms based upon the formula? 10. So this is how we can go from hydrogen atoms that are given to moles of caffeine. The reason we need to do this is because it's asking what is the total mass of caffeine in the sample. It's not asking how much does this hydrogen weigh. It's asking for caffeine. So we need to figure out that relationship between the actual atoms to the actual, the molecule itself. So I'll start with what's given, and you'll see that really we're just working backwards from the previous question, hydrogen atoms. All right, so I'm going to convert atoms to moles. So 6.022 times 10 to the 23 atoms, so in this case hydrogen atoms, equals 1 mole of hydrogen. So now I'm in the unit of hydrogen, so now I can use that nifty equality that I just came up with. So 10 moles of hydrogen is 1 mole of caffeine. And now that I'm in moles of caffeine, I can just use the molar mass that we have for caffeine within there. So 1 mole of caffeine will tell me the mass of the whole dang thing. So 194 grams within there. Okay, and so my answer here is 138 grams of caffeine. So the big thing to recognize here is that we are given hydrogen atoms in the entire sample, so we need to come up with this relationship that can relate hydrogen atoms, moles of hydrogen atoms to the moles of the actual sample caffeine that we have. So definitely I have some examples of practice ones. Basically, they're all the same questions, just with different substances. So you can do these ones on your own. So the thing to recognize here is, how many of each atom are within your chemical formula, and this relationship can help you interconvert between, molecules to individual atoms and grams of your substance. Okay, so that wraps up molar masses and using the mole for Chapter 3. So the idea that, we just used molar mass of caffeine like a bunch. So I would be hard pressed to see that an exam question would just straight up ask you, what is the molar mass of blah? We would never ask that. But you still need to know how to use that skill. And calculate molar mass and how to interconvert between moles of a substance and grams of a substance. You will be using that constantly for all of chemistry, all right? So knowing that idea that as long as you have access to the periodic table, you can calculate the molar mass of anything and interconvert between grams of that substance and moles of that substance. That is assumed for the rest of your time in chemistry, all right? So keeping all of that in mind, we will use that to do some different types of experimental application to determining the composition of different substances. So let's think back to the idea of empirical formulas that we talked about in Chapter 2, all right? Empirical formula is just the simplest ratio of atoms in a compound. So let's just remember that. Like when we looked at hydrazine, right? Hydrazine, N2H4, that was the molecular formula, that was the true composition of the thing. But we recognized, we can simplify those those subscripts by 2, and H2 would be the empirical formula. And then, you might have looked at me funny and be like, what's the point of an empirical formula? I will tell you the point now of an empirical formula. Empirical means by experiment. So when scientists, chemists were trying to determine the composition of unknown substances, they couldn't go straight to a molecular formula using this process that I'm about to show you. The only thing they could calculate was the empirical formula. All right, so keep that in mind for this section, that when we go through percent compositions and calculate formulas, we are calculating the empirical formula. We oftentimes need an additional piece of information to get to our molecular formula, but sometimes they're the same if the multiplier is 1. Okay, so within there, when we look at empirical formula, you see that those subscripts there, so nitrogen, there's 1 nitrogen, 2 hydrogens. This is our mole ratio. It's telling us what is the simplest ratio between our atoms. Okay, so this is, I have most of the steps there for you. Here are just some additional tips to determining a empirical formula from percent composition. So if you recall from last lecture, we talked about you can take the molar mass of a substance if you know its chemical formula, and you can calculate the percent composition or percent mass of each element within that chemical formula, right? So I think we did what, iron 3 oxide, and we calculated, okay, there are 2 iron atoms for every one, iron 3 oxide formula unit. So we did the 2 irons over the whole molar mass to get the percent mass of iron. So we're taking those percentages, those masses, because this is something that scientists could actually measure in the laboratory. They might have an unknown substance. They figure out, 65% of the mass of the sample is iron, and the rest of it is oxygen. So using this method, they could calculate the empirical formula, essentially the mole ratio of the atoms in the substance. So the big strategy, and this works like for any empirical formula calculation, is you need to get grams. So I think that's the first step. Express your composition in grams of all of the elements. Oftentimes, values are given in percentages. So you could just assume those, you have a 100-gram sample, and all those percentages become grams. Once you have all your elements in grams, you convert all of those gram amounts of each element to a mole amount. All right, so to go to grams to moles of an element, what do we use? Molar mass, all right? That's what we just learned the last section. Once you get the mole amounts for each element, this is what I call, determine the mole ratio. So what I do is I look for the smallest number that I just calculated and divide all the values by that number. And there's a reason why. It ensures that we have an integer value for that mole ratio, and then you express the empirical formula. I think it's just best if we do an example, all right? So here is my example. We have a compound, and here's its percent composition. There's 3 different elements: carbon, hydrogen, and oxygen. So really basically the strategy is express everything in grams, convert everything to moles, get your mole ratio, get your empirical formula. So right now we are given percentages. Okay, so the first step is get grams. So when you're given percentages, a good strategy is just assume you have 100 grams of sample. If you have a 100-gram sample and 68.54% of it is carbon, how many grams of carbon do you have? 68.54. So this is what I mean. Just turn all the percentages to grams, and then you're just assuming you have a 100 gram sample. All right, so within there, I did the first 2, so then the last one, we have 22.83 grams of oxygen in my sample. And so next, we have everything in grams. So we did the first step. Now we need to do the second step, convert everything to moles. All right, so here we convert each individual element to moles of that element. So you have to make sure you use the correct molar mass for that substance. So for carbon, the molar mass, this is not a number you have to memorize. Where would you find the molar mass of carbon? Over there, yes. But I bet you probably will just memorize the number because you will use it so often. It is 12.01 grams is 1 mole. So make sure that your units here match up to cancel out. So I want to put the gram amount on the bottom, moles up top. And I like to be very specific here and say moles of carbon. And then you can stick that in your calculator. I like to write everything out first and then just pick up my calculator once. So let's do the same thing for hydrogen. Again, use molar mass of hydrogen. It's 1.008 grams, 1 mole of hydrogen. That gives me moles of hydrogen. Next is moles of oxygen, so 16.00 grams, 1 mole of oxygen equals blah. And so if you put all of that into your calculator, you get that this sample has 5.7 moles of carbon, 8.56 moles of hydrogen, and 1.43 moles of oxygen. All right, so does that mean that my compound is C5.7, H8.56, O 1.43? Does that look like a chemical formula that you've ever seen? No. All right, and so this is where step 3 comes in. All right, it's what I like to call, okay, look at all the mole amounts you just got, identify the smallest one. Which one's the smallest number? 1.43. And so the trick here is you divide all the numbers by 1.43. 1.43. What this does is ensures at least one of the numbers is an integer, right? So the moles of oxygen becomes an integer because we're dividing that number by itself, 1 mole of oxygen. And so when you do this, you get something like 3.99 moles of carbon when I divide by 1.43, and then 5.99 moles of hydrogen. And so those two numbers basically round up to 4 and 5, or sorry, 4 and 6. Come on. No, what did I do? 4 and 6. And so now these numbers, this mole ratio, is something that I can actually express as an empirical formula. All right, so this would be something like C4H6O. That would be my empirical formula. And I'll go back a slide real quick because I kind of skipped over it. So step 3, we just did step 3 where we divided everything by the smallest number to get that mole ratio. All of those numbers were basically whole numbers, like 3.99, 5.99, those round to whole numbers. But what if the numbers aren't whole? All right, so that's a little trick that we need to do if the numbers that come out of that step 3, aren't whole. So that's what step 4 is. If what you get out is more like a fraction, then we can't round. So for example, if the number you get from step 3 is really close to a whole number, like 1.95, you can round that to 2 when it's really close. Or if you get like 2.02, then that rounds to 2. But if you get a number like 2.501, someone might be like, oh, that rounds to 3, but it doesn't round to 3. 2.5 or 2.501 is very, very close to 2.5. And so if you get one of your mole ratio values as a fraction, then you multiply all the numbers, all the mole ratio numbers by an integer to get rid of that fraction. So for example, 2.5, what number would we multiply that to get rid of the fraction or the decimal? 2. So you'd multiply that by 2, but you'd have to multiply all of them by 2. All of them by 2. Right, so let's just like pretend if this one, if like instead of 5.99, if that was like 5.5, then you would multiply everything by 2, so the ratio would then be 8, 11, and then 2, for example, but that's not true for this. All right, how about this one? 2.33, can I round that down to 2? No, 2.33, 0.33 is like a third. Right? So this number would be better if we just multiplied it by 3, and so 2.33 times 3 is 7. And so remember, you multiply all those ratios by 3. What about 2.66? How could we get rid of that fraction? You also multiply by 3. I think the value you get, sometimes you just have to guess and check, and that's okay. That's 8. So times 3 is 8. All right. So just practice. I have a lot of weird ones in there also within here that can help you practice this step 4 if they're not integers. Okay, so let's do one more. Another problem with empirical formulas. So we have a compound here. It has this much phosphorus and this much oxygen. All right, so in the previous example, I gave you percent compositions. I told you have to assume 100 gram samples. Those percentages go into grams. But this one, remember our first step for empirical formulas? The first step is express all the elements in grams. These are already given in grams. So we just start with those numbers. Cool, right? Then we don't have to do as much work. So after you express them all in grams, our next step is to express them as moles, right? So we use the molar masses respectively for those elements. So phosphorus, I even give it to you, 30.97 grams, 1 mole. Of phosphorus, 16 grams oxygen. See, I like to set it all up and then just pick up my calculator once. All right, and so this will give me mole amounts of phosphorus and oxygen in the sample. So there we go. Mole of phosphorus. I always like to be specific. Mole of oxygen. Okay, is that my empirical formula? P.141, O 0.351. No, it's not. We need to express that as a whole number or integer. So the trick to do it is identify which value is the smallest one. In this case, it is phosphorus. So if you divide both of them by 0.141, you get 1 mole of phosphorus, and this is 2.49 moles of oxygen. All right, so is that my empirical formula? P10 2.5? No, it is not. So can 2.49 round down to 2? No, it can't. So a better way to do this is multiply everything by 2 to get rid of that fraction there. So if we multiply everything by 2, we get 2 phosphoruses, 2 moles of phosphorus, and we get 5 moles of oxygen. So then our empirical formula is P2O5. Is that the answer? Yes, it is. All right, so that's an example where you get a fraction at the end. All right, how do we feel about this? It's super systematic. It works every single time. Grams, moles, find the smallest one, mole ratio, empirical formula. It's very repetitive. Once you know how to do one, you know how to do all of them. Okay, all right, so how else can we manipulate these percent compositions? So we just calculated the empirical formula, the simplest ratio of atoms, all right? So, well, what if we wanted to calculate the molecular formula of hydrazine, right? If we did the percent composition to empirical formula for hydrazine, we would get the value NH2. How did scientists figure out that hydrazine is actually N2H4? Well, this is the extra bit of information that we need in order to answer questions like this. So in order to calculate an empirical formula, a molecular formula, we need to know the molar mass of the full molecule. If we know the empirical formula, so the simplest ratio, and if we know the molar mass of the full molecule, we can essentially figure out, okay, how can we scale up our empirical formula? What is the multiplier to figure out what is the full molecular formula there? So this is the extra bit of information. So I want you to recognize how these questions can be asked on an examination, all right? The question will look almost exactly like an empirical formula calculation. It'll say something like this, like you have this much sample, this much phosphorus, this much oxygen. But they'll add an extra tidbit. They'll say, and the molar mass of the whole molecule is this. What is the molecular formula? So I'm trying to show you that molecular formula questions are worded exactly like an empirical formula question. It's just one additional piece of information. And the thing is they were worked the exact same way. In order to calculate the molecular formula, you need the empirical, the simplest formula first. And then we work up to the next one. All right, so this is how we do it. So if we take that empirical formula that we got before, C4H6O, in this question, it says, okay, your molecular weight of a compound, so the molar mass or molecular weight of the full compound is around 140 grams per mole. That's the weight of the full molecule. The empirical formula is C4H6O. So we have the 2 bits of information we need. We have the empirical, we have the molar mass. All right, and it says, okay, what's the molecular formula? And so the strategy here is, I know that the molecular formula will be some multiple of the empirical, right? Either times 2, times 3, times 4. We are given the mass of the whole molecule. So if we compare the mass of the empirical to the mass of the whole molecule, we can figure out what that multiplier is. And so this, you can kind of just do back of envelope type of calculation. Carbon is 12 grams, so that's 48 grams, plus hydrogen's like 1, so that's 6, plus oxygen is 16. Oh, did I do this? Did I write the number down? Is that about? Okay, I'll calculate it. 6 plus 48 plus 6 plus 16, 70. All right, so that empirical formula is about 70. I don't need the exact number. And then we ask ourselves, okay, how can this mass scale up to 140? What would the multiplier need to be? 2. So whatever we do to the molar masses to make it match, we do to the formula. So that means the molecular formula is C8H12O2. So that's just a little tidbit at the end. Yes?
How do we determine or find the molecular formula if just theoretically not any problem?
Oh, theoretically, it's exactly what we're doing right now. This is how scientists did it. They determined the percent composition of a substance. Oh, with a okay. So then, in order to get the molecular formula, what was the second piece of information we need? What did we need?
Molecular
Mass, the molecular weight, right? So do you remember our mass spectrums from chapter 2? Chapter 2, where we sent chlorine atoms through the charged chlorine atoms through a magnetic field and they split. That's how. So we send big molecules, they're charged through a magnet and then they split and we can figure out their masses that way. So that's the extra bit of information. But as long as we know the empirical and the molar mass, we can scale up and that's how we do it. Okay, so it's just kind of like tacking something on at the end there. So be very, very aware what a question is asking. Is it asking for empirical or is it asking for a molecular formula? Okay, so if that wasn't enough math and ideas with mole ratios, to just kind of bring another type of question into this analysis, another type of empirical formula question we can ask is, we don't give you percent compositions, because I'll be honest with you, there's no instrument in the lab that you can put a sample in and it tells you percent of each element. That's not really how chemists did it. What they did was this: they did combustion analysis. They burned the thing and they measured the weight of the stuff that came off of it. All right, so this is more typical of what a scientist would do, is a combustion analysis. And this is how we approach it. And it works with the exact same principle of what we just did, that we get the number of moles of each element in the compound to get our mole ratio. We're still working off that principle. We're just going to get the moles of each of the elements in a different way with combustion analysis. So if you recall, when we write a combustion reaction, our products are CO2 and H2O. So when doing combustion analysis, we're working off the principle of conservation of mass. If we burn something, all right, with carbon, hydrogen, and oxygen, all of the moles of carbon in our sample goes where? It goes to CO2. All the hydrogen in our sample goes where? In water. So if we know the mass of CO2 and the mass of water, we can figure out, okay, how many moles of carbon and hydrogen did we start with? Cool. I will note here, you do not need to know the coefficients. This is not a balanced chemical formula. We are working off the basis of conservation of mass. We don't actually need the coefficients in this idea here. So carbon and hydrogen come from CO2 and water. That's what I say here. All right. Oxygen we need to treat a little bit differently, and I'll show you a different example. So just have this relationship. All the carbon is there. All the hydrogen is there. We need to do something special with oxygen. So here's the strategy for calculating empirical formulas for combustion analysis. Thankfully, the end is basically the same as what we just did before. The big difference is that instead of starting with like mass of carbon or like mass of hydrogen, we are given a mass of CO2 instead. But we can figure out how many moles of carbon are in a certain amount of CO2. So instead of starting with percentages of each element, we're given a mass of CO2 and a mass of water instead. And from there, we can get the mole amounts of carbon and hydrogen. So that is steps 1 and 2. Convert the grams of CO2 and water to moles of carbon and moles of hydrogen. Step 3 is the hard part. If oxygen is present in the substance, we need to do something a little bit tricky to get moles of oxygen. And the reasoning is, if we look at this reaction, can we say the same thing? So we said all the carbon goes to CO2. The oxygen in our sample goes to both carbon and water. And then someone might say, oh, well, if we just add up the mass of oxygen from CO2 and water, can't we get it the same way? But also look at this. When we burn something, we're adding oxygen. So we can't use this direct approach like we can for carbon and hydrogen. The way we get the moles of oxygen is we need the total mass of the sample, and whatever is left over is the mass of oxygen, and from there we can calculate moles of oxygen. I will just show you an example, okay? So here's another way to think about it. Take the mass of CO2 and water produced, convert it to moles of CO2 and water, convert that to moles of carbon and hydrogen in the sample. If your sample is just carbon and hydrogen, you can stop there. But if there is oxygen present, you need to go one step further to figure out what is the mass of oxygen to then get moles of oxygen. Yeah? This is the same as before. It's, you get the moles of the carbon, hydrogen, and oxygen, you find the smallest one, divide, get your empirical formula. It's the same steps as before. The only new stuff are these first 3 steps. All right, okay, I think I just want to do an example. Okay, so we have a carbon and hydrogen sample. We combust it in air. It makes this much CO2, this much water. So this is my strategy here. You take carbon. Remember, the goal is to get, okay, how many moles of carbon are there? How many moles of hydrogen are there? Just like other empirical formulas. So we start with CO2, so 64.60 grams of CO2. How do I get that to moles of CO2? Molar mass. So the molar mass of CO2, I'll just tell you, is 44.01 grams, is 1 mole of CO2. Is that moles of carbon yet? No. So how do we get to moles of carbon? We look at the formula. How many carbon atoms are in one CO2 molecule? 1. So it's a 1-to-1 ratio, and you might be snickering back there thinking, Dr. Wynn, she's just multiplying by 1, she doesn't need to do that. But this step is really important because the goal here is to get to moles of carbon, moles of hydrogen, of the elements, not these products that we're starting with. All right, so I like to write this step, and I'll show you why in the next line. So if we do that math, we can get moles of carbon. It's just a regular empirical formula question after that. So let's do water. How much water do we have? 27.68 grams of water. So we use the molar mass of water here to get moles of water, and that's 18.02 grams is 1 mole of water. Okay, are we in moles of hydrogen yet? No, we're not. So we have to look at the formula for water. How many moles of hydrogen are in 1 mole of water? 2. If a student's going to mess up, they're going to forget this too. If you're going to mess up in a combustion analysis, you'll forget this too. That's where it is, like 9 times out of 10, that you'll forget this too, if your answer doesn't match mine. So again, the idea is we need to get the moles of each element. So we can't forget this step, that we have to multiply by 2 to get the number of moles of hydrogen, because there's 2 hydrogens in each water molecule. So then once you do that, okay, where are we? All right, we get 1.536 moles of carbon and 3.307 moles of hydrogen. Is that my empirical formula? No. So now it's exactly like we did before. We have moles of each element. So what? We identify the smallest one, right? So the carbon one, so we divide that by 1.536, both of them, 1.536. So you get that there is 1 carbon for every 2 hydrogens. And so the empirical formula here will be CH2. So see how the ending there is exactly like we did before? It's this setup. Before, we started with grams of carbon, went to moles of carbon directly. So in this case, we're kind of doing it indirectly because we are given masses of CO2 and water instead. But I want you to recognize that these questions are very, very similar. The steps are very, very similar. Okay, so there we go. So if you look at the strategy down here, when it's just carbon and hydrogen, you stop here. You don't have to do this last step, right? Because once we have moles of carbon, moles of hydrogen, we can get the mole ratio. But things get kind of tricky. Oh, okay. One more thing. So this CH2 is what kind of formula again? Empirical, okay. So let's say the molecule, the combustion analysis revealed that it was CH2, right? We did a different experiment, mass spec, to determine that the molar mass of the full molecule is 56 grams per mole, right? So we can use that piece of information to help us get the molecular formula. So the target mass is 56 grams per mole. How much does CH2 weigh? About 14 grams per mole. And so you can ask yourself, okay, what do I need to scale up by? Or you can just do 56 over 14, and you get that, what is the multiplier? 4. So it's times 4. So that means the molecular formula is C4H8. So C4H8, this is our molecular formula. This tells us the composition of the substance, right? It just tells us the number of carbon atoms and hydrogen atoms in the substance. So what we just did, combustion analysis together with the molar mass to get molecular formula. Do we know which one of these the compound is? No, because those pictures depict what about the molecule? Structure, right? And so we just calculated composition. So we would need a completely different thing to figure out the structure. So all of these structures actually share the same composition, C4H8. We can't actually distinguish them. Okay. All right, let's do one more. All right, so another combustion analysis, but this time we have oxygen. So we got to do that little weird thing at the end. All right, but it starts the exact same. We start with CO2, H2O, convert to moles of each carbon and hydrogen. So let's do that. So 38.28 grams of CO2, 44.01 grams of CO2, 1 mole of CO2. 1 mole of CO2 is, 1 mole of carbon. Do the same thing for water. So 23.49 grams of H2O. 18.2 grams is 1 mole of water. This last step, super, super important. I think whenever I write a key, I always highlight it, all right? 1 mole of water, that's not moles of hydrogen. We need to include that 2 there. So 1 mole of H2O is actually 2 moles of hydrogen, okay? I will highlight it because it's just that important. Okay, and so you stick that into your, so this is how I like to do it when there's oxygen. I start at the exact same. I need to get moles of carbon and hydrogen in order to get an empirical formula. So I'll kind of do a stopgap right here. Oops, I should have showed you this. I'll do a stopgap right here and get moles of each of those substances. So that is 0.868 moles of carbon and 2.606 moles of hydrogen. But we need to get moles of oxygen too. So what I just did right there is exactly the same as we did in the previous question. Same exact setup. The problem is we need moles of oxygen also. And how we do that is we essentially figure out, okay, how much mass does the carbon and hydrogen occupy? Anything that's left over is oxygen. And it tells us the mass of our sample here. All right, so the mass of the sample is 20 grams. So if we figure out, okay, mass of carbon and the mass of hydrogen, we can figure out what's left over. So oftentimes, instead of going straight to grams of CO2 to grams of carbon, I will stopgap right here and then just do the extra, okay, 1 mole of carbon is what, 12.01 grams. Hydrogen, 1 mole of hydrogen is 1.008 grams. Equals blah, and then I figure out how much both of those weigh. So for carbon, this weighs 10.45 grams of carbon, and then hydrogen is 2.627 grams, those 2 values. And so anything left over, so our whole sample is 20 grams, anything that's left over is oxygen. Do you see that? So we got to do something a little bit funny to get oxygen. This is the funny thing we have to do. All right, and so what's left over? If you subtract both those numbers from 20, you get that there is 6.92 grams of oxygen. I will admit, this is hard. There's a lot of moving parts here. Yeah.
Like 1 mole of oxygen into where the 2 mole of H is and get the same thing without having to do that extra step?
So this is a lot of students think that, and I think that's a very astute thing when you think of where the oxygen is coming from. So you're looking at the oxygens from the CO2 and the water, right? So when we add the masses of these oxygens, so what I'm trying to say is the moles of the oxygen in the sample is not tied to the oxygens in these two substances. The reasoning is because we are reacting it with other oxygens. So when we think about, like, take inventory of the oxygen on the product side, we don't know if it came from the actual thing or if it came from the surrounding air. Does that make sense? Okay, all right. All right, so let's go back. So does everyone know how I got this 6.92? Okay, all right, good. All right, so then we keep going. Yeah, okay, then 16.00 grams, 1 mole of oxygen, and then bam, that gives me moles of oxygen, 0.437 moles of oxygen. And so this, we have all the pieces needed to get the empirical formula with moles of carbon, moles of hydrogen, moles of oxygen. See why I kind of stopped in the middle of the calculation and then did one more step? So I didn't have to like go back, right? So these are all the pieces we need to get the empirical formula. That's it. All right, and it's exact same as the previous one. What number do we divide all of those by? The 0.437. So I think the empirical formula is C2H6O. Good, good, okay. Very similar steps. Got to do something funny with oxygen. Okay, so what we just went over with empirical formulas really exemplifies the use of molar mass of substances, thinking, okay, is it a molar mass of a compound, of an actual element? All right, so I have so many practice problems. It's this, you'll see, it's the exact same process over and over and over for a lot of these empirical formulas. Okay, so the last part of this section. So we might not finish today, but that's okay. We can do it on Wednesday, and remember, the rest of Wednesday we're just going to do practice problems. My question is, what chapter do we think is the hardest? 2? 3? 3, okay, all right, I just wanted to know, okay. All right, so let's work with numbers even more, all right? Okay, now we're gonna fight each other over the hardest chapters. Okay, so reaction stoichiometry. So the beginning of this chapter, we talked about balancing reactions. Those coefficients have meaning. They have meaning. That's what stoichiometry is. Stoichiometry is using those coefficients to figure out, okay, how much reactant you need, how much product is made. And so the big idea here with stoichiometry, you need to be in the unit of moles in order to use the coefficients on a balanced chemical equation. So you see a balanced chemical equation here, right? So these coefficients are relating the combination of these substances. 2 moles of hydrogen gas combines with 1 mole of O2 gas to give 2 moles of water. So essentially you're building inequality coming from these coefficients within here. So within stoichiometry, make sure that you understand molar masses. All right, because in order to use those coefficients, we need to be in the unit of moles. All right, so let's keep going. So so solving stoichiometry problems, you need to work in moles. I like to say, in order to use the coefficients to get on the bus of the balanced chemical equation, you need to be in the unit of moles of one of the substances. All right, so here's that general method. All right, and you can read that. But the big idea here is these coefficients tell us an equality that we can use in dimensional analysis. So what I said is that these coefficients are related. 1 mole of O2 will produce how many moles of water? 2. So I can write an equality about that. 1 mole of O2 equals 2 moles of H2O. That's an equality I can write. Or I can write this one. 2 moles of H2 equals 2 moles of H2O. So if we can write this equality, we can set up our conversion factor depending on what we, where we need to go from there. All right, so I think let's just try this out. So how many moles of H2 would be formed from the complete reaction of 8 moles of potassium in excess water? So we're thinking, okay, we're going from potassium to hydrogen. So let's write a equality that relates those two. 2 moles of potassium equals 1 mole of hydrogen. You see where I got that? That's just using the coefficients on the periodic table, or sorry, on the balanced chemical equation. So let's start with what's given, 8 moles of potassium. We want to figure out how many moles of hydrogen are produced. So if we take the equality we just wrote, 2 moles of potassium will go on the bottom. 1 mole of H2 will go on the top. So then how many moles of hydrogen are produced here? 4. 4 moles. So the big skill, 4.0 moles of H2. The big skill here is being able to look at these coefficients and come up with an equality to then use as conversion factors, right? If we wanted to go to water to H2, it would just be, 2 to 1, right? And depending on what units we're canceling, we'll change how we set up our conversion factor there. But, setting up this equality, if you've gotten on my whole spiel with, setting up equalities, you'll see how all of this comes together. So what we just did here was probably the simplest way to relate a reactant to a product. Do we have anything in lab that can measure moles of something? No. How do we measure matter? Mass. Right. So this is a more realistic way to think about this question. Let's do the same calculation, but this time I say, okay, 15 grams of potassium reacts. How much grams of H2 is produced? The middle part is still the same. What we did up here, so this step right here, this is stoichiometry. That 1 mole H2, 2 moles potassium. That is stoichiometry. So this is a different way to go about it, but we're given grams of substances. But that's fine, because we can just use molar masses to convert to moles. All right, and so that's what you see here. Start with what's given, grams of potassium, go to moles of potassium with the molar mass. Then right here, to get from moles of potassium to hydrogen, we use stoichiometry. So that's using the coefficients on the equation, and then go to our desired substance, grams of hydrogen here. So I will start with what's given, so 15 grams of potassium. I use the molar mass, so 39.098 grams is 1 mole of potassium. So now that I'm moles of potassium, I can get on the bus to use the coefficients. So I see here that 2 moles of K is 1 mole of H2, sorry. And note here, see how I wrote the molar masses of potassium and hydrogen gas? Note here that even though the coefficient is 2 potassiums, when I look at the molar mass, I just have the molar mass of one potassium, 1 mole of potassium. I don't take into account the two coefficient, because I take into account that 2 later in stoichiometry. That's a common misconception I see. Are we done? No. Where do we need to go? Grams. So this is where we use that last idea. 1 mole of H2 is 2.016 grams of H2. And the answer is 0.387 grams of H2. So these steps, going from grams to moles of something else to grams, you will probably, I would say, do that at least 100 times before the midterm. Okay, because all of stoichiometry, all of reaction stoichiometry is based upon that idea, going from grams, moles to grams. I'm going to keep teaching. All right, so in these last reactions, the funny wording here is that we said potassium reacted in excess water, meaning that, see how there's 2 reactants here? There's potassium and water. We assumed all of the potassium got converted to this the reaction went forward and made this product. We had that assumption because we said, oh, it's in excess water. There's essentially unlimited water within there. So this brings us to the idea of like actual real chemistry where something is typically limiting. I was going to show a demo, but that's okay. It'll stay good for Wednesday when we finish up. The idea of limiting reactants. When we combine two things to make something else, something is going to run out first. And so my idea here is, you know, if we make sandwiches, right? A cheese sandwich is a slice of cheese, 2 things of bread makes a sandwich, right? So if I have 18 slices of cheese and 30 slices of bread, how many sandwiches can I make? 15. Think about how you got the number 15. Did everyone get 15, that you can make 15 sandwiches? Do we see how we can get 15 sandwiches from that chemical formula? Think about how the steps. How did you get 15? Talk to your neighbor about that. Explain to them how you got 15. Be super specific. All right, so I hear some really good conversations, but class is over. So we will come back to this conversation. You know, until Wednesday, think about how you got 15 sandwiches, come up with a better answer. We'll come back here on Wednesday and finish that up.